Alright, last problem of the last section of operational amplifier chapter. First of all, congratulations. Congratulations on sticking with us on this intriguing chapter. Many students find it difficult. That is because they do not invest the time and effort to understand. But you are different. You understood all the basics. Not only that, if you have noticed, in this chapter, we have been working on multiple examples, at least 2 examples for each of the sections, just to demystify the topic, just to make sure you thoroughly understand the operational amplifiers. Okay? Without further ado, let's go into the chapter. Okay? Example problem actually. So here is the problem, right? Here is the last problem that we are going to look at in the operational amplifier chapter. This is again, think about it, this is really a difference amplifier because 2 inputs are applied to the inverting terminal and then more inputs are applied to the non-inverting terminal. Okay? Because you do that, it is a difference amplifier. Input is applied both to the inverting terminal and the non-inverting terminal. Plus, there is a negative feedback configuration. Okay, so we want to analyze this circuit. Now, it's a numerical problem. There's not a lot of derivations in this. Okay, we are simply going to plug in the numbers. VA value is given, VB is given, VC is given, and VD is given. So all these input voltages, okay, their values are given. We are simply asked to find out the value of VO. Okay, so let's do that. How do we go about doing that? Okay, if only I knew the value of Vn, the node voltage there, I could write KCL at that node. But not to worry, we have seen that if we can find out the value of Vp, that should equal value of Vn because of virtual short, right? So let's try to write KCL at Vp, okay, just so we can find the value of Vp. The current going in this branch is Vp minus Vc, which is given to be 3 volts divided by 30 kilo ohms. Okay, plus the current going in this branch is Vp minus Vd, which is given to be 4 volts divided by 20 kilo ohms. And don't forget this branch over here. Okay, all of this is the same node. Okay, all of that is the same node, right? So let's not forget the third branch there as well. Let's see. The third branch current going down is what? Vp minus 0, because this is connected to ground, divided by 20 kilo ohms. According to Kirchhoff's current law, all the currents leaving, if you add them up, it equates 0. Very good. Now Vp, let's multiply the whole thing by 60 kilo ohms, the numerator, both sides of the equation. Okay, so doing that, there is a factor of 2 over here, 2 Vp minus 3 V plus this term gets a factor of 3, right? Because it is multiplied by 60 and divided by 20. So 3 times Vp minus 4V plus this term gets a factor of what? 3 again, 3Vp. Okay, 3Vp, all of that equals 0. Now separate out all of this, we get let's see, Vp minus 3 volts plus by 20 kilo ohms. Is that 20 kilo ohms? Yes, 20 kilo ohms plus 3, 6 plus 3, 8. So 6 plus 12. So this is going to be 2Vp plus another 3Vp plus another 3Vp minus 6 minus 12. Okay, so it turns out that 8Vp is 18 volts. Okay, so Vp is really 18 by 8, which comes out to be 2.25 volts. Okay, first part of the solution. Okay, we are glad we got a value because this 2.25 volts that we just calculated, that shows up here as well. We need this value to be able to write KCL. Okay, so now let's write KCL, step number 2. Okay, so let's write KCL at node Vn. Okay, once we want to write the value KCL at node Vn, we look at how many currents, 1, 2, 3, 4. Okay, the current going in here is 0. Okay, not surprisingly. Okay, so let's look at the current flowing in this branch, Vn minus Va over 20k. Okay, the current flowing in the bottom branch is Vn minus Vb over 18k. Okay, and the current flowing in the right branch, okay, Vn minus Vo all divided by 180k. Okay, those are the three. Simply to add them up and say they are all equals, that sum equals to 0. Okay, so Vn, okay, Vn minus Va by 20k plus Vn by 18k. Okay, so Vn minus Vb over 18k. Okay, that's 18 kilo ohms. That's right there. Okay, where are we? 18k plus Vn minus Vo over 180k. You see, I have done these equations so many times that I almost memorized these numbers. Okay, so the current flowing in this branch, Vn minus Vo by 180k. That's what I plugged in for the last term. Okay, so that's what I plugged in for the last term. Now we know Va value is given to be 1. Okay, let me refresh. Va is 1, Vb is 2. So we know these values, and we just figured out that Vn value 2.25. Okay, let's see, 2.25 minus V is 1 by 20k plus Vn is again 2.25 and Vb is 2 volts, that's the given value 80k, plus Vn 2.25 minus Vo over 180k is 0. Okay, simple, simple, simple. I'm going to just align this to the center. Okay, all of this. So multiply both sides of the equation by 180k. Okay, so 180k by 20k, this first term multiplied by 180 divided by 20, so 9 times plus this term is multiplied by 180 divided by 18, so 10 times 0.25 plus the 180k cancels, so 2.25 okay, 2.25 minus VO equals to 0. Okay, so 9 point, is that so? 9 plus 2.25. Okay, so that's, I think that's the value for 9 times 1.25 plus 2.5 coming out of this fraction plus 2.25 equals to VO. Okay, so sum them up, 2.5 and these two terms actually add up to 4.5. So 4.5 and 2.5 is what? 7. 7 plus 9 is 16. Okay, so all of this, you plug it into your calculator. You plug all of this into your calculator. All of this comes to how much? There it is. Okay, that's the result that we wanted to see. We wanted to calculate the V out. Okay, for the values of VA, VB, VC, and VD that are given in the problem. Okay, so congratulations again. It has been a very steep learning curve with operational amplifiers. Okay, practice more. Practice makes perfect. Okay, so practice more. The more problems you see in different contexts, the more comfort level you'll get with operational amplifiers, or for that matter, any circuit. We will see you in the next chapter. We are looking forward to that.